When physicists talk about the multiverse, they are not borrowing ideas from science fiction. They are trying to solve real, stubborn problems inside their own equations. The word multiverse gets thrown around a lot. Movies use it, podcasts use it, and almost every time it means something like parallel realities where your alternate self made different choices. That version is mostly harmless entertainment. But here is what rarely gets explained. The actual scientific case for multiple universes did not come from imagination. It came from three separate corners of physics, each arriving at a similar uncomfortable conclusion for completely different reasons. And those reasons are worth understanding, because they change how you think about what science is even allowed to say. Let us start with the problem that forced physicists to take this seriously in the first place. In the 1970s, the standard model of cosmology had two enormous headaches. The first is called the horizon problem. Look at opposite ends of the observable universe. Two regions so far apart that under normal physics they could never have exchanged information or energy. Yet the temperature of the cosmic microwave background, the faint afterglow of the Big Bang, is almost identical in both directions. Identical to roughly 1 part in 100,000. That should not happen unless something coordinated them early on. The second headache is the flatness problem. The geometry of the universe is almost perfectly flat, like an infinite sheet, rather than a curved sphere or saddle. Flat geometry is an unstable configuration. Even a tiny deviation in the early universe would have amplified dramatically over time. The fact that it is still flat today means the initial conditions were tuned to extraordinary precision. Neither of these problems was fatal on their own, but together they suggested the standard Big Bang story was missing something. In 1980, Alan Guth proposed inflation, the idea that the very early universe underwent a brief and violent period of exponential expansion, stretching space faster than light. Inflation solved both problems in one move. A huge, smoothed-out region expands so fast that all of it ends up at the same temperature, and that same stretching irons out any initial curvature until what we see looks flat. It was an elegant fix, but it came with an unexpected consequence. In 1982, André Linde and Andreas Albrecht independently refined the inflation model to fix an earlier technical flaw called the graceful exit problem. Their refinement worked, but it also opened a door. The quantum fields driving inflation are not perfectly uniform, they fluctuate, and in some regions those fluctuations cause inflation to keep going, rather than stop. This is eternal inflation. The universe as a whole never fully stops inflating. Instead, pockets of space periodically drop out of that inflationary state through a process called quantum tunneling, each one forming what looks like a bubble universe with its own physical constants, its own temperature, its own future. Eternal inflation predicts an infinite number of these bubble universes, continuously spawning across a vast inflationary background. And according to cosmologists, this picture of global space-time structure is currently the most widely accepted framework in the field. That is one route to the multiverse. Here is a completely different one. In 1957, Hugh Everett submitted his PhD dissertation at Princeton. He was not trying to invent parallel universes. He was trying to solve a problem inside quantum mechanics itself. Quantum mechanics is extraordinarily precise. It predicts experimental outcomes better than any other theory in the history of science. But it has a strange feature. Before you measure a quantum system, it exists in a superposition of multiple possible states. The moment you measure it, it appears to collapse into just one. The dominant interpretation at the time, known as Copenhagen, essentially said, do not ask what happens during measurement, just use the math and get your answer. Everett found that unsatisfying. He showed that if you treat the wave function as literally real and let it evolve according to quantum mechanics without any collapse, every possible outcome of a measurement actually occurs. They just occur in separate, non-interacting branches of the universal wave function. Each branch is equally real. There is no collapse, just branching. This is the many worlds interpretation, and it proposes that every quantum measurement physically realizes all its outcomes across separate universe branches. Most physicists ignored it for decades. Today it is taken seriously enough that some regard it as the most mathematically natural reading of quantum mechanics. The third route comes from string theory. String theory is an attempt to unify gravity with quantum mechanics by replacing point particles with tiny vibrating strings. It requires extra spatial dimensions, 6 or 7 beyond the 3 we experience. Those extra dimensions have to be curled up, compactified, into shapes too small to detect. The problem is, there are an astronomically large number of ways to do that compactification, each one yielding a different set of physical constants. Around 2003 to 2005, Juan Maldacena and colleagues worked through the implications. The string theory landscape contains roughly 10 to the power of 500 possible vacuum solutions. That is not a typo. 500 zeros. Each vacuum corresponds to a different kind of universe with different physics. Now here is why that number matters beyond being enormous. One of the deepest mysteries in physics is the cosmological constant, the energy density of empty space that drives the universe's accelerating expansion. Quantum field theory predicts it should be roughly 10 to the power of 120 times larger than what we actually measure. That is the worst prediction in the history of physics. The string landscape, combined with eternal inflation creating bubble universes, offers a possible answer. If you have 10 to the 500 different universes with different values of the cosmological constant, some of them will have small values purely by chance, and those are the ones where galaxies, stars, and observers can exist to ask the question. This is called the anthropic argument, and it makes a lot of physicists deeply uncomfortable. Here is why. An argument that says we see this value because otherwise we would not exist here to see, it does not actually predict anything new. It explains after the fact. And that brings us to what many consider the most important question in this entire discussion. In the early 1930s, philosopher Karl Popper formalized what most scientists had always felt intuitively. A theory is scientific if and only if it can, in principle, be falsified. It has to make predictions you could test and potentially prove wrong. The multiverse, in most of its versions, seems to fail that test. The other bubbles in eternal inflation are beyond our observable horizon. The other branches in many worlds do not interact with ours. The other vacua in the string landscape are permanently inaccessible. In 2014, physicists George Ellis and Joe Silk raised a pointed warning. Some of their colleagues were beginning to argue that a theory elegant enough, or necessary enough, should not require experimental confirmation. Ellis and Silk saw this as a genuine threat to the scientific tradition. That same year, Carlo Rovelli stated directly that multiverse theories do not deserve serious scientific consideration if they cannot be falsified. But not everyone agrees that falsifiability is the final word. Some argue that a theory can still be scientific if it makes predictions about things we can observe, even if the other universes themselves remain hidden. Eternal inflation, for instance, predicts a specific statistical pattern in the cosmic microwave background. There is a 10-degree cold spot in the CMB, roughly 70 microkelvin colder than the average temperature of 2.7 Kelvin, that some researchers have proposed could be the imprint of a collision between our bubble universe and another. The evidence is not conclusive. Most cosmologists attribute the cold spot to statistical fluctuation, but the fact that the prediction exists at all means the debate is not simply about untestable metaphysics. So where does that leave us? The multiverse is not one idea. It is 3 distinct theoretical pressures arising from cosmology, quantum mechanics, and particle physics, all pointing in a similar direction without being designed to do so. Whether that convergence reflects something true about reality or just something true about the limits of our current theories is a question physics has not answered. What is clear is that the most interesting battle here is not between science and science fiction. It is between 2 camps of serious scientists who disagree about what science is even allowed to claim when the evidence runs out. If you enjoyed this video, consider subscribing to the channel.